Alright, so today we're going to finish looking at section 7.2. And for the rest of the week we'll do 7.3 and 7.4. We have a review day on Thursday. 7.4 is on trig identities. And sometimes that can be a little bit tough. So I think it'll be good to probably spend a second day on that or whatever else we need to use that day for to get ready for the test. Alright, so the last part of this section, there's two things they talk about. The first thing is how can we take a formula that has trig in it, okay, something like that, and convert it to a formula that doesn't have any trig. Okay. So we know that that formula I just showed you had trig because you saw sines and cosines in it. So our goal is to somehow get rid of the sines and cosines and turn it into just algebra. Numbers, variables, plus, minus, square roots, squares, anything you want except sines, cosines, tangents, secants, cosecants, and cotangents. You want to get rid of all those somehow. And with certain expressions, you can do that pretty easily. Okay, sometimes if you were to just make one up randomly, it might not work. The ones I have are designed to work out nicely. And when we do this, we're going to have two functions. We're going to have one inside the other. Okay, so just as an example, cosine is the inside function, sine is the outside function, or inverse cosine. So the key is we're going to start with the inner trig function, and we're going to draw a diagram on it. Okay, so for the type of problem we're going to start with, we're going to draw a diagram that represents the inner trig function. You're going to kind of forget about the outer one. The outer one doesn't even really matter until the very end of the problem. So you can almost just block it out for now. And what's going to help us to draw that diagram is that if the inner trig function is inverse trig, like it's going to be in our first example, we're going to try to rewrite that using regular trig. Okay, so we're just going to do something to both sides so we can rewrite it with regular trig. It's not necessary, but I think if you've never done it before, it's going to help you to draw the diagram a little easier than if you don't do it. So as we go through this, keep in mind the Pythagorean Theorem, and that's really all we need to be concerned about. What's going to come up in all of these problems is you're going to be drawing a diagram, you're going to know two of the sides, and you're going to have to figure out the third side. So keep in mind the Pythagorean Theorem. Sometimes we'll be figuring out the third side and it'll be numeric. Sometimes it's just going to be all letters. Okay, first example, it's just going to be all letters. Okay, so here's our formula. It says the sine of the inverse cosine of v. The v is not important. It could be vx, q, just whatever the variable is. Okay, so when I'm done, I want to have a formula that's just algebra. No sine, no cosine. Okay, so you can have anything you want except sines and cosines. Generally, you have things that are squared, and you have square roots. And that comes from the Pythagorean Theorem. Okay, so the directions say start with the inside trig function. Okay, so I'm going to forget about sine for now. I don't even need to worry about that until the very last step. Okay, so inverse cosine. Now, on the calculator, if I type in like 0.5, and I put that in inverse cosine, I get an answer of 1.05. What is that? I mean, it's radians, but what does that represent? If it's measured in radians, that 1.05 is representing an, you know what? Angle. It's an angle. Okay, so anytime you do inverse trig, you press enter, the answer that you get represents an angle. So this thing, it represents an angle, and we usually use a Greek letter to represent an angle. So for now, I'm going to say if you take the inverse cosine of v, you're going to get an angle. I don't know what it will be, but I'll just call it theta. Any questions on that first step? Okay, I'm not going to write this every time. I just wrote it the first time so you could see. All right, so now it says, if the inner function contains inverse trig, we're going to rewrite it with regular trig. All right, so what could I take on both sides so that the inverse cosine cancels out and I'm left with just a regular trig function and it'll be on the other side? How can we get rid of inverse cosine? Well, think about what is inverse cosine? It's not a formula. I'm looking for something specific. Inverse cosine is a same thing with inverse sine, inverse tangent, square root, square. These are all examples of, what do we call those things? They're all things you have to plug something into, right? So it's not a formula, but it's a, think about, like if you had something like this, and you were to graph that, that's an example of a what? Yeah? It's a function, right? That's a function. Inverse cosine is a function. Square root is a function. So the only way you can cancel out a function is with another function. If you want to cancel square rooting, you use the inverse of it, squaring. If you want to cancel, like in calculus, if you want to differentiate, the opposite of it is integrate. They're inverse functions. So I want to know basically what would cancel out inverse cosine.
Cosine.
Cosine. So we take the cosine of what's on the left. Okay, I'm not multiplying because you can't multiply by a function. Multiplication is only used with letters and numbers. Okay, but you can take all of this and basically plug it into cosine. Think of cosine as a box, and you're dropping inverse cosine into it. Okay? And we have to do it on the other side. So again, think of cosine as a box, and we're dropping theta into that box. We're going to see what comes out when we're done. Okay. Well, when you plug inverse cosine into regular cosine, it cancels. And then when you plug theta into cosine, not really much you can do. So you get v equals cosine theta. Now, we're going to set up a right triangle diagram. And the diagram is going to represent what we have written right there. Doesn't matter where you put theta. You can put it wherever you want. But now that I put it there, I have to label two of the sides. And this fact that I'm pointing to tells me two of the sides. Okay. First of all, how about Caleb? It says v equals, and what's my trig function?
Cosine theta.
Cosine theta. So when I'm dealing with cosine, what two sides does cosine involve?
Adjacent and hypotenuse.
Adjacent and hypotenuse. So we need to label the adjacent and the hypotenuse in a certain way so that when you divide them, adjacent divided by hypotenuse, you get v as the answer. Can anybody give me a way that I could label the adjacent side and the hypotenuse so that when you divide them, you get v as the answer? And there's really, literally an infinite amount of ways to do it, but we want to try to do it the simplest way we can. Yep.
V1.
Okay, where would you put the v?
V would be the adjacent, v the hypotenuse.
Yep. V would be the adjacent, and 1 would be the hypotenuse. Perfect. So now this picture represents the statement up above. The cosine of theta is v over 1. adjacent over hypotenuse. That's exactly what the equation says. Now, we have to go back and pay attention to the outside function. Now we're at the very end. We want the sine of that diagram we just drew. Okay, we just drew a diagram for what I circled. We want the sine. Sine involves, Megan, which two sides?
Opposite and hypotenuse.
Opposite and hypotenuse. Well, the problem is I don't know the opposite. But I have a right triangle. I have two of the sides. So Gracie, how can I find the third side?
Wait, can you re-ask the question?
How would you find the third side in that right triangle? It's not going to be numeric. It'll have variables in it.
Could you use sine?
Well, we can't use a trig function because we don't have enough information to do it. The Pythagorean Theorem. Okay, we can use the Pythagorean Theorem. And you can set it up however you want, but I would just say, temporarily, you can call it x. We're going to cross that out in a second. But Sam, can you set up the Pythagorean Theorem using the three labels I have in that picture?
B squared plus x squared equals x squared. Oh no, plus x squared.
Yep. There we go. So we had everything squared just on the wrong, we had one of them on the wrong side. But v squared plus x squared equals 1 squared. Perfect. And now solve for x. So we get x squared equals 1 minus v squared. And now I have the squaring function. I got to get rid of that. So Sam, how would I get x by itself here?
You square root it.
Yeah, take the square root and take the square root. So I get x equals the square root of 1 minus v squared. Now I have all the sides labeled, and now I can answer the question, what is the sine of that picture? It's opposite over hypotenuse. It's the square root of 1 minus v squared over 1. So that's a formula that if you plug in a number on the right side of the formula, and you plug a number in on the trig on the left side, you're going to get exactly the same answer. Any questions on that? How could I verify, or not algebraically, but what's another way I could verify that what's on the left and what's on the right are the same? Yeah? Yeah, I could graph them. Graph them to see if they look the same. Now, graphing doesn't prove anything. All that graphing does is suggest that if they look the same, you probably did it right. Okay, so we have sine of inverse cosine of x and square root of 1 minus x squared. Again, this step is not necessary. It's just double checking that we did it right. I'm going to do zoom 7. And then I'll zoom in a little more because it drew it kind of quick. You might not have seen it. That's the left side. That was the sine of the inverse cosine. And there's the right side. Any questions on that? Which one drew faster? The left side or the right side? If you watched it as it actually did it. Yeah?
The right side.
The right side. So if you do anything with computers or programming, and you want to talk about like efficiency, if you can write it using the left-hand side or the right-hand side, it's going to be a lot more efficient to write it on the right-hand side because it can draw it faster. In terms of calculations, the calculator views the right-hand side as something simpler than the left-hand side. Okay, the calculator had to do a lot more work on the left-hand side, and you can watch it if you watch the timing. Okay, it was much, much faster to draw the right-hand side. Okay. So any questions about that one? All right, so let's try have another one of those. Okay, In these kind of problems where you have regular trig on the outside, inverse on the inside, they all follow the same pattern. You do exactly the same steps every time. Right, so Tessa, could you tell me, what am I going to start with here? Yep, and what's inside the parentheses there? Yep, the inverse sign. Okay, so we're going to start with the inverse sign, and we're going to set it equal to something. Rebecca, can you tell me what I'm going to set it equal to? Yep, because we know that's going to equal an angle in a diagram. We don't know what the angle is, so just call it theta. Caleb, can you tell me next step? What do I want to do with that?
You, since it's an inverse trig, you want to make it regular.
Okay.
So you would take the sine of both sides.
Exactly. Take the sine of both sides, and what will that give me?
Sine of theta.
V equals sine theta. Now I have an equation, but I want to represent that information in a different way. Okay, so Shauna, how can I represent that in a different way? Yep, you can draw a right triangle. And Tanya, does it matter where I put theta in that triangle? No, you can put theta wherever you want. But now we have to label two sides. Dylan, what two sides am I going to label in that triangle?
Opposite and hypotenuse.
Yes, I'm going to label the opposite and the hypotenuse. And I have to label them in such a way so that when I divide opposite by hypotenuse, I get that as an answer. Okay, you can label it any way you want as long as it comes out to V. So Gracie, what could I label the opposite and the hypotenuse as? V and 1, yep. V and 1. And this is pretty much the same diagram we just had. So using Pythagorean Theorem, you're going to get the square root of 1 minus v squared again. Okay, any questions on that? Now we have to go back up to the original problem. They want tangent. Leo, tangent involves which two sides?
Opposite over adjacent.
Opposite over adjacent. So that's equal to v divided by the square root of 1 minus v squared. Now technically we've answered the question. Write an algebraic expression. I've done that. But what's wrong with that algebraic expression that we might not normally leave it that way? Megan?
There's the square root under the denominator.
Yeah, we normally wouldn't want to leave that square root in the denominator. So what would I multiply the top and bottom by to fix it so the root can be in the top, it just can't be in the bottom? Yep.
You multiply by the square root of 1 minus v squared.
Yeah. Multiply by the square root of 1 minus v squared. And square root of 1 minus v squared. And in the top, you just get v square root of 1 minus v squared. And in the bottom, 1 minus v squared. So you can graph what's on the left in y1, put what's in the right in y2 if you wanted, and you would see they look the same. The right-hand side, it's a little harder to type in this time because you have a fraction, so you'd have to be careful with parentheses. But that is correct. Any questions on that? And what you have right here, okay, don't erase it on your notes, but it doesn't have to be as simple as just a single letter. It could be something like, x minus 3. And if it was an x minus 3, well, all you'd have to do, everywhere in this diagram you had a v, change it to an x minus 3. So this would become an x minus 3, and then I could do the Pythagorean Theorem, get the third side, and so on. Okay. So if it's a single letter, great. If it's not a single letter, just use whatever they give you, do out the Pythagorean Theorem with it, and find the third side. Okay. A lot of times it will be a single letter. Sometimes it won't. All right, does anyone need to see another one of that type? That's the regular on the outside, inverse on the inside. Okay, so it's pretty much the same thing. This one's a little different. This is evaluate. So evaluate means when you're done, you should have a number as an answer. But they want us to do it without a calculator. So what that means is the answer has to come out nice. So it's the inverse sine of the tangent of 3 pi over 4. Okay, if you think PEM dash, you're going to start with what's inside. Forget about inverse sine for now. Let's start with the tangent of 3 pi over 4. See if we can figure out that. 3 pi over 4 is in radians. For what I'm going to do next, some people might find it easier to do in degrees. So what is 3 pi over 4 in degrees? And if you're not sure, think of like what pi over 4 is, and then you're tripling that. Yep.
Would it be 135 degrees?
Right. Okay, so pi over 4 is a 45-degree angle. Triple it is 135. Right. So that's a multiple of 45. Any angle that's a multiple of 30 or 45, we can draw what kind of circle to figure out that answer. We spent about a week on this type of trigonometry. It wasn't right triangle trig. It was something with a circle. Yeah? Unit circle. So now use unit circle trig and find the tangent of 135. If you don't have it memorized. Does anybody have it memorized? If we do, we don't have to do that. But I'm guessing not. So let's do it. Let's draw your circle. Remember, on a unit circle, the radius is 1. That's 180, 90, 135. It's exactly halfway between 90 and 180. Now here's where we do have to have something memorized. What kind of triangle did I just draw? What are the angles on it? Yeah? A right triangle? Yeah. Can you be more specific? 245s, yes. It's a 45, 45, 90. And if the hypotenuse is 1, because it's the radius of the circle, does anybody remember the length of the two legs in a 45, 45, 90? It involves something with a square root. Leo?
Isn't the square root of the hypotenuse?
Well, that would mean that each leg would be 1. Then it would be equilateral. So it's not the square root of the hypotenuse. They are the same though. Whatever one is, so is the other one. If we don't know it, we can figure it out by solving this problem. Use Pythagorean Theorem. But hopefully we don't have to do that. Yeah?
Like the square root of 2.
Square root of 2, it's part of it.
Yeah, I know the other side.
Square root of 2 over 2. So each leg is root 2 over 2. Now we've just drawn a diagram and we can find the tangent. There's your reference point right there. Tangent is opposite over adjacent. Now, I wrote root 2 over 2 for each of the legs, but what do you want to be careful about because you're in quadrant 2? Whenever you do unit circle trig in a quadrant besides quadrant 1. Yeah?
Negatives.
You got to be careful with negatives. Technically, if you want to put it in so you don't forget it, the x is negative. So, if tangent is opposite divided by adjacent, what would that come out to here? What's opposite divided by adjacent? Yeah. -1. So now we've just figured out what I just underlined. The inverse side of the tangent of 3 pi over 4 as a simpler question is the inverse sine of negative 1. Okay, any question on that? Now, there's a couple ways you can think about this part. If you like inverse trig and you want to think of it that way, that's fine. Or if inverse trig confuses you and you rather think of it in terms of regular trig, we can do that too. So down here, I'm going to put inverse sine of negative 1 equals, and what did I say earlier? Whenever you do inverse trig, the answer is always an what? Anytime we do inverse trig and then you hit enter, the number that you get represents, it's an angle. So we know that that's going to be equal to an angle. So if you don't want to think of it in inverse trig, don't. Think of it in regular trig. Take the sine of each side. You could do something like this. And now the question basically is the sine of what angle is negative 1. If you can think of the answer to that question, it's the same as the answer to that question up above. So ask yourself where the sine is negative 1. A couple ways you can think about that. You can think about it as a picture. Here's a picture of sine. And think about where you would have to go on the x-axis to hit negative 1 on the y-axis. That's the answer. Or you could look at it on the unit circle. We know that sine on the unit circle is the y value. So think about what angle you would have to be at to go down 1 and hit a y value of negative 1. So you can think of it as a circle or as a graph. But can anybody tell me what angle would have a sine of negative 1? Leo?
Be 270, right?
Yeah. Can you explain how you figured that out?
The graph.
You use the graph?
Yeah.
Okay. So negative 1 is right there. And what did you do? How did you?
Well, I knew the graph peaked at intervals of 90 degrees.
Right. So if you mark all the quarter points, right, the high and the low, they all occur at multiples of 90. That's pi over 2, pi, 3 pi over 2, and 2 pi. So as long as he knows that those coordinates on the graph, 3 pi over 2 is where you hit negative 1, that's the answer to the question. So 3 pi over 2. Or you could have put 270 degrees. That's where the y value is negative 1. Right, so that kind of combines lots of different thoughts. We got to know a little bit about unit circle trig to figure out the inside first, and then the outside, there's lots of different ways to think about it. I tend to think about it in terms of a graph.
On the test, will you take either radians or degrees?
Yeah, unless the problem says here, I'm really more concerned with how you got there. Did you figure out the inside first using unit circle trig somehow, and then use that information to get the outside part? But radians or degrees would be fine. Yep. Okay, any questions on that one? And as I said when we started it, it has to work out nice. If the inside function came out to an answer of like 0.75 or something, like a weird number, it's not going to be very easy to figure out where this graph hits 0.75. It's easy to figure out where it hits 1, negative 1, and 0. That's pretty much it, okay? Without a calculator. Okay, so it'll always work out special with a problem like that. All right, let's try this one. Is this the same type as the last one? Looking at the structure of the problem, is it the same structure? You Abby?
The inverse is in the parentheses.
Right, the inverse is inside. Well, that's more like what we did right here. And it's actually easier than these because it's a number. It's numeric. So it's the same process that we followed before, except now when you end up setting up a right triangle diagram, it's all going to be numbers. You're not going to have any letters in it at all. All right, so let's try that one. Okay, so we have the cosine of the inverse tangent of 1/2. Okay, so start with that inside function. And, well, Sam, what am I going to set the inside function equal to?
Theta.
Yeah, we know that anytime you do inverse trig, the answer is an angle. Now, if you can draw the right triangle diagram right from that step, go for it. If you need to rewrite it with regular trig, you can do that too. So let's rewrite it with regular trig. So Julianne, what would I do on both sides to get rid of inverse tangent?
You would multiply them by 2.
You would do what with tangent?
You would take tangent from each side.
Exactly. Take the tangent of each side. Take the tangent on the left. Take the tangent of the right. And now, Tessa, what does that leave me with?
Tangent of theta equals 1/2.
Yep. So we have tangent theta on the right equals 1/2. Now we can set up right triangle diagram. Trevor, in my right triangle diagram, what two sides am I labeling?
Opposite and adjacent.
Yep, opposite and adjacent. And what would you make the opposite? How long?
2.
Okay. Can you tell me what's the definition of tangent again?
Is it opposite over adjacent?
Opposite over adjacent. So opposite over adjacent. So how long would you make the opposite side?
1.
1. And then adjacent?
2.
2. There you go. And now using Pythagorean Theorem, we could get our hypotenuse. What's the hypotenuse here as a square root? Well, yeah, Leo? Square root of 5. Okay. Now we're at the point we go back up. Look at the original outside function. They want the cosine of that. Okay. So the cosine of my diagram. How about Caleb? What's my cosine there?
2 over the square root of 5.
Yep. And can you fix that for me?
So it'd be 2 square roots of 5 over 5.
Perfect. So we figured out that whole problem without ever really knowing that. What's the inverse tangent of 1/2? I don't know. We never figured that out. We didn't need to. All I wanted was the cosine of inverse tangent of 1/2. I didn't really want to know inverse tangent of 1/2 by itself. Okay, so when inverse is on the inside, you never have to evaluate that. You just draw the diagram, you use Pythagorean Theorem. And they would look for an exact answer here, not as a decimal, without a root in the bottom, okay, on the test. Questions on that one? All right. That's another one very similar to the one we just did. Any questions on how to do that? So the inverse is on the inside, so you draw your diagram, use Pythagorean Theorem, and then go from there. All right, so a couple reminders about solving trig equations. This kind of leads into what we're going to do in section 7.3 tomorrow. So when you're solving a trig equation, there are always, well, if there's one solution, there's infinite. Okay. Think of like a sine wave. If I asked you where that sine wave hits 1, well, draw a horizontal line at 1. It's going to hit there. It's going to hit there. It's going to hit there. It's going to keep hitting 1 infinitely many times. Now, does anybody remember how often you get a solution? So if I draw this a little nicer, and then I want to know where that hits, say, 0.5. Well, if that's 1, 0.5 is about right there. So it's going to hit here, here, and then again, here, and here. The two that I just drew in black, those answers are repeats. The two in red are also repeats. And again, all the way down. How far apart are the two black dots in general? Yeah? It could be. We're not sure because we don't have any labels on the x-axis. But you're on to the right idea. Yep. They're a period apart. If the period is 2 pi, then 2 pi. But they basically are one wavelength apart, one period. So keep that in mind. If we're going to solve it graphically, remember the calculator doesn't have buttons for secant, cosecant, and cotangent. So you would have to type that in using a reciprocal identity. 1 over tangent is cotangent. 1 over cosine is your secant. 1 over sine, cosecant. Okay, so you might have to use a reciprocal identity to type in one of those trig functions. And we'll just try a couple easy ones. The ones we're going to look at today pretty much just have a single trig function equal to a single number. Tomorrow we're going to get into an equation maybe with multiple trig functions in it, like sine plus cosine equals 0.6, instead of just sine equals 0.6. Okay, that's a little simpler. Also, tomorrow what we're going to look at is higher powers. So that's just sine to the first power, if you want to put it in. We're going to look at, like, what about sine cubed, or sine squared, or even combining. What about sine squared plus sine cubed equals 0.5? Okay, it gets a little more complicated to solve, and the graph starts to get a little bit more interesting. Okay, but for today, we'll just look at basic trig function. Right, let's do it algebraically first, and then we'll double check our answer on the calculator. Okay, so the goal here is to get x by itself. What could I do on both sides to cancel out the sine function and get x by itself? Yeah.
Take the arc sine.
Yeah, take the arc sine or inverse sine of what's on the left and do the same thing on the right. Okay, I'll do this in degrees because I think it'll help something make a little more sense with a diagram. I'm going to draw that ASTC diagram in a second. And we've looked at that before, so hopefully we remember what that is. Okay, so the inverse sine of 0.6. Okay, I'm going to change to degrees for this problem. And it's not going to be a nice answer. It's going to be a decimal. And we get an angle of 36.87 degrees. Okay, any questions on that? So what we just found there, that's one of the answers. There's 2. And the reason I know there's 2 is because the original problem says sine equals positive 0.6. Well, if I look at my diagram, what quadrant did I just get an answer? 36.87. Yep. Well, yes, those are where the two answers are going to be, but where is the first answer specifically? That's quadrant 1. So I just got an answer there. So because that angle is in quadrant 1, we talked about this before, if you do inverse sine, that is called your reference angle. Okay, so that 30, whatever it is, 36.87, that's my reference angle. Now, to find the second answer, I need to do two things. First, I need to figure out the quadrant I need to be in. It's either 2, 3, or 4. And then, once I know the quadrant, use the correct formula, either for 2, 3, or 4. Okay, so let's look at it. Rebecca already told us sine is positive in quadrant 2. So I'm going to go back and look at my formula. For quadrant 2, it's 180 minus my reference angle. So I've got 36.87. Just subtract that from 180, and you get 143.13. Those are the two answers. Okay, so now let's double check by graphing it and see what happens. Okay, what we're basically going to get is a sine wave and a horizontal line, and it's going to hit it twice. It's going to look very similar to this picture right here. But I only want to focus on one section. There's no need to look at other answers later on. Okay? I just want to focus on the first section. And I'm going to come back to this idea in a second, which we already touched on. Okay, but let's just make sure those two numbers are right. All right, so I'm going to graph sine of x. I'm going to graph 0.6. I should have cleared that first. And now, I know that earlier someone said that the cycle or the period is 0 to 2 pi. I'm in degrees. So that's 0 to how much for one cycle? Yep.
360.
360. I know that the graph of sine doesn't go above 1 or below -1. So -2 to 2 is perfect. Okay, so here's one cycle of my sine wave. We're going to see the horizontal line in a second. And now what would we calculate to get the two answers? Calculate the intersection. So second calc, intersect. I'm closer to the second one, so I'm just going to do the second one. And we know we got the second one from the first one. So if this is right, then the first one is probably right too. 143.13. 143.13. And then if you calculate the other one, it will be 36.87 right there. Now, it doesn't just say to find the solutions in the first quadrant. It says to list them all. Well, this wave is about to intersect again right over here. So what would I have to put on that answer to represent all solutions? Because how often is that answer going to reoccur? Every period. So we have to put plus 2 pi n. N is an integer. So, oh, I'm sorry, we're in degrees, so plus 360. That means if you add one multiple of 360 to that, you will get the next answer. If you add two multiples of 360, you get the one after that. You can add any multiple of 360. And the same thing here. And technically, you can subtract multiples of 360. If you wanted to get the answer before that one, just pretend n was -1. If you go 360 degrees before 36.87, you'll get another answer off the left side of the screen. Okay. Any questions on that one? All right, so let's finish up with this one. So I want to know where the cotangent of x equals 2.5. And this one, we'll just do graphically. Now, before I draw it, what quadrants is cotangent positive in? Yep.
1, 4.
1 and which one?
4.
4 is where cosine is positive. So the C stands for cosine in quadrant 4. Yep. 3. Right? If tangent is positive, so is its reciprocal. Flipping it doesn't change the sign. So we would expect answers in quadrant 1 and quadrant 3. All right. So let's graph tangent of x, or cotangent. So I have to do 1 divided by tangent. I want to know where it equals 2.5. Okay, I'm just going to do zoom 7 so you can get kind of a broad look at it. So in a second, we're going to have a line at 2.5. It's going to hit it a bunch of times. You generally want to find the first positive answer, which is right there. Second calc, intersect. Just get your cursor somewhat close to that intersection. 21, all right, we're still in degrees. 21.80 degrees. Now, before I continue, what's the period of cotangent? Anybody remember how often that one repeats? Well, let's look at let's set our window to something easy to look at. Let's set it from 0 to 360. From 0 to 360, how many times is the graph repeating? Oh, Megan? Twice. So what's the period of it then? Pi, yeah, or 180. So this graph repeats every 180 degrees. That's why in a 0 to 360, you see it twice. So plus 180 n. Now, Caleb told us earlier we would expect the other answer to this to be in quadrant 3. To find an answer in quadrant 3, it's 180 plus your reference angle. So let's take our reference angle, 21.8, and add it to 180. 8 plus 180. Let's just do it in my head because the calculator is having trouble. 201.8. That's the other answer. And what would I have to put on the end of that? Yep.
Plus 368.
Careful, 360 is not the period here. 180. Okay. Any thoughts about what I've written here and what I've written here? Yeah?
The first answer already includes the second answer.
Right. If you list all the answers in that box, they are going to be repeats of all the answers in the thing below. They're the same thing. So really you should recognize that and realize all you have to write is what's in the box. What you wrote down below is a repeat. Okay? And that usually happens with tangent and cotangent. If you were to graph this properly, from 0 to 180, you would see that when you draw it in one cycle, there is only one answer. It's right there. There are not two answers per period, because the graph of tangent is different than sine and cosine. Okay? So keep that in mind when you do it. Don't just kind of go through it every time and say, oh, I got to get the second answer. Maybe you don't have to. Okay? If it's tangent or cotangent, usually there's not a second answer. Sine, cosine, secant, cosecant, there is. Any questions on that? Okay, so tomorrow we'll look at solving equations that have higher powers and also combining multiple trig functions in the same problem. Okay, so the homework is on 394, okay, and it's 37, 38, 41, 42, and 44 to 53. Okay, so you've got about 15 minutes or so. So you've got a little bit of time you can get started. If you do have any questions, let me know. If you don't have a graphing calculator at home, I would suggest starting with the ones that you need that for now, because there's a lot you don't.